Hello gentlemen, welcome to our video on section 6.5, reaction diagrams and conservation of energy. Now in our last video, you were introduced to reaction diagrams and we analyzed them in terms of just reactants starting at a particular energy point and progressing through a course of a chemical reaction to form products that have a different energy. Now today we're going to still keep our focus on energy, but it will be in terms of how energy is conserved through that reaction process. It's really important to know that energy is conserved in every chemical reaction, just like you learned in your physics classes, that energy is conserved in any type of mechanical process. In terms of chemistry, energy is conserved in the molecular collision. So when two molecules hit one another, that's how chemical reaction happens in general. Molecules have to collide with enough energy to actually form the products. In that process, energy is conserved. Now, so that happens through molecular collision. Let's talk about that journey in this video. So, a few key things, Molecules have a certain amount of kinetic energy. As they approach one another, they have kinetic energy, but they also have electron clouds on their exteriors. Well, the electron cloud is most of the atom. So electron cloud on the exterior, they start to repel one another. As they repel, those molecules slow down. So their velocity decreases, and thus their kinetic energy decreases. Because as you learned in physics, kinetic energy is based on mass and the square of the velocity. So as velocity decreases, your kinetic energy decreases as well. Those particles come towards one another. The repulsive forces of the electron clouds, both being negative, makes them slow down, and kinetic energy decreases. Now, you learn that kinetic energy has a counterpart, and that's potential energy. When kinetic energy decreases, potential energy increases. That's the stored energy. And if you remember your reaction diagrams, on the y-axis, we mentioned it was potential energy there. And that's the potential energy we're going to be covering in this video lecture. So that stored energy begins to increase. And that's a noted relationship between kinetic energy and potential energy. It's an inverse relationship. They're inversely proportional. So in this case, this is the energy being conserved. What was once kinetic energy is now being turned into potential energy. The equation representing that conservation is here. Kinetic energy plus potential energy equals your total energy oftentimes called mechanical energy. Now the example we're going to look at today is called the Haber process. We'll talk more about what that means in class, but we have nitrogen gas reacting with hydrogen gas. Those are your reactants. They're going to form your activated complex at your transition state at the top of our reaction diagram, and then they're going to form our products. Let's look at that diagram together. Now here is our generic XY graph where we're going to populate our reaction diagram. Now these reactants, N2 and H2, start at some point. We'll call it, here. At this point, this is where they are coming towards one another. They both have their individual kinetic energies coming towards one another, and the electron clouds start to repel. Here in green, when the electron clouds start to repel, that high kinetic energy that they had before begins to diminish, and the potential energy starts to increase. That's represented here. We have potential energy in our y-axis. As they come closer to one another, potential energy begins to rise because they're repelling, but then they hit a point up here. And that is when they collide. So they come towards one another with really fast kinetic energy. They repel, boom. They still hit one another. If they're not going fast enough and the repulsion is too strong, they will stop and not even collide, and you have no chemical reaction. But here, we're saying given enough kinetic energy initially, they will come together, come closer, potential energy increases, represented by the increased slope here, and then at the top of the curve, this is where they collide. So down in red here, molecules collide at the peak of the diagram. And that is called your transition state. That's when you form your activated complex and the atoms rearrange to begin to form your products. This is when potential energy is at its highest point. There. Okay, at the apex of the diagram, that's when kinetic energy is at its lowest point. You have mostly potential, not much kinetic. If you do have a successful collision, the product is formed. And those formed molecules, which have their own electron clouds now, they've rearranged activated complexes, now formed a product. Now those products are now close to one another. They have their own electron clouds. They begin to repel one another and go away from each other. When they do, when they start going away from one another, they're gaining speed. They're gaining kinetic energy. If I gain kinetic energy, that means I have to lose potential energy. That's why the graph decreases in its slope. New product is formed, those molecules start to repel one another, and you decrease until we get to a certain energy here. We'll talk about the leveling out and why that happens in class. But this represents the energy of my product. In this case, NH3. So this is the journey energetically of the molecules. As they approach, kinetic energy decreases, potential energy increases, they collide. Given they have enough energy during that collision, they'll have a chemical reaction together. The atoms will be rearranged to form the product. That product will then repel one another, decreasing the potential energy, increasing the kinetic energy, thus forming this reaction diagram. Now, a few key points here. The highest point on that graph from the reactants up. In your last video, you defined that as your activation energy. This activation energy is going to change based on the molecules you have to begin with, based on the bonds that they have. If something has just single bonds, maybe it won't require as much energy. If there are triple bonds in a molecule, it might require more energy, so you have a higher peak there. And the space in between my reactants here and my product. In our last video, we defined that as your enthalpy of reaction or your heat of reaction. Oftentimes given by the symbol of delta H. That's the change of heat from reactants to products. So gentlemen, please take notes on this video and come prepared to talk about how energy is conserved in chemical reactions. Adios.